So, what did we talk about last week? I think, you know, the tasks on our wiki, they made it quite obvious what we talked about last week. Because I spelled it out again, but what was it? Binary, yeah? We talked about connection-oriented, connectionless communication. We talked about the decimal number system. We talked about the binary number system. So, are we all clear on how the binary number system works? Yeah? And we have those recurring numbers, you know, 8, 16, 32, 64, 128, 2 to the power of something else. Yeah? So if you buy a mobile phone, it might have 32 or 64 gigabytes of memory. It wouldn't have 47 or something like that. It's because the way computers store and transmit information, the binary system is just very useful for that. If we want to send electricity over a copper wire, we can send electricity or we cannot send electricity. I'm simplifying again, you know, there are more complicated things like Manchester code, for example. But in our simplification, that certainly works. You know, we send something, we don't send something over the copper wire. We want to store information on the hard disk, we make a magnetic field, we don't make one. Again, I'm simplifying, but you know, that's the way we can store data as zeros and ones, and we transmit data as zeros and ones. So in the end, we talked about how the internet works, we talked about packets. Yeah. What's an internet packet? We talked about connectionless communication. Yeah. So if we talk about electronic communication in the past, for example, you making a phone call, what did you have to do? I'm looking at you because you said you worked in telecoms, did you?
Well, yeah, you have to phone the number you want to phone.
Yeah. And then you create a connection.
Constant connection.
Yeah.
And you communicate both ways with an open connection.
Yeah. So that's called connection oriented because you create a connection first. But we can also communicate over copper wires without having to create a connection, and that's how the internet does it. That was connectionless communication. How did that work? Who was doing connectionless communication on the wiki? Difficult for you because you weren't here last week. So, connectionless communication, yeah. Who wants to remind us all how it worked? Any volunteers?
It goes like through, so there's like different pathways with don't choose the fastest or
Yeah. So our message is split up into little packets, and I think as an example, we looked at a Korean web page and we tried to figure out which way it goes around the globe. But because of UCLA's firewall, that wasn't too successful. So you sending a big file by email, or you downloading a video that you watch on Netflix, anything, basically we transmit over the internet, will be split in little packets. And like a letter, those little packets get marked where they're from, where they're going to. And that way we can be much more efficient with the way we use those copper wires. Before, connection-oriented communication, I want to call somebody, I need to create that connection, and that copper wire is reserved for me. Connectionless communication means the same copper wire could be used by 10, 50, 100 different parties. They all send their own packets over the copper wire, and because you know there are only a few bits, you can pack quite a few onto the copper wire. In the end, electricity over the copper wire. Difficult question. What speed is it traveling with? Nearly with what speed? But let's round it up a bit. There are a few constants in physics or in the world in general. So there's a good chance electricity over a copper wire doesn't travel with a randomly made up number like 50 miles an hour, while that it travels with one of the constants that exist in the world.
Speed of light?
Yeah, yeah. So electricity over copper wire more or less travels with the speed of light. And if you make your zeros and your ones very short, you can put a lot of zeros and ones into, for example, 1 second of communication. What's a good broadband speed these days? Yeah, then what would be a good speed? What unit would be measured in? Megabits? Good. Megabits per second. And what would be a good speed these days? Yeah. If you take Virgin, you can get 150 in Preston, but let's go with 40. Yeah. Okay, 40 megabits per second. What does mega stand for? What does kilo stand for? Kilo is 1,000, yeah. And I think I talked about it last week. Kilo, is 1,000 in the sense of kilogram. It's 10 to the power of 3. In a computer system, even though officially we shouldn't call it kilo, everybody calls it kilo. Kilo could also be 2 to the power of 10. So kilo could either refer to 1,000 or 1,024. And a mega, how many kilos in a mega? Yeah. So 1 mega is, either 1,000 or 1,024 kilo. It depends on which system you work with. So if it's about electricity, a megawatt would be 1,000 times 1,000. What's that? A million, yeah. So electricity, a megawatt would be 1,000,000 watts. In computing, it could be 1,000 different bits. In computing, use different things. If you buy a hard disk, a magnetic hard disk, an old-fashioned hard disk, they would probably use this system because the numbers look slightly better in this system. But normally in computing, everything works in that way. If they use this system in computing, it's usually for marketing purposes because the numbers look slightly better. So 100 megabits per second, how many bits is that per second? Yeah? Also, actually, sorry, we said 40 megabits, so that's 40 million bits per second. Yeah? So in 1 second, we can transmit 40 million bits over our little copper wire. And you might not need it all for yourself. You're just sending an email or whatever you might be doing. You only need a tiny fraction. And we're just talking about the line between your house and the next internet point. Between the different internet points, the connections would be even, much faster. We would be talking about gigabits and numbers like that. Yeah, this is a slightly old. This is from 2011. But if we look at, how different continents are connected in 2011, for example, 6 years ago, Europe to the outside, to the other continents, was connected with 27,000 gigabits per second, so 27 terabits per second. Let's have a look. It's not so clear on this slide. Yeah. So maybe not so easy to read with that light here, but we can see, for example, Europe is very well connected to the USA. Europe, actually, it looks like it's also well connected to Asia Pacific. But if you follow all those connections, and they're basically transoceanic cables, if you follow all those connections, you see that most of them are actually going to Istanbul and to Turkey. And Turkey itself, is not that well connected to East Asia, for example. So even though it looks like Europe is very well connected with East Asia, it's not that well connected with East Asia just because of the geography. Yeah. There's not much going through Russia. North of Russia, it's quite difficult to have cables. South of Russia, the geography just isn't there. And we're not using satellites either. Satellites might sound like sexy technology, but it's not really very suitable for internet traffic. Where is my little picture? Yeah. This is Earth. Yeah. Satellites. This is roughly, of course. Oh yeah, you can't see it. It changed again. Yeah. So if this is Earth, satellites are really far away. Of course, the satellite would be high. And the problem again is what speed do the signals travel with? Speed of light. Yeah. You could have something flying very close to Earth. Yeah. I'm sure we all heard of the ISS. Who does not know what the ISS is? Yeah. So can somebody explain what the ISS is to your classmate? Yeah, so what is it?
It's like a ball, isn't it? Outside of the Earth, like for astronauts and that.
Yeah. And it's usually serviced from, I think from Kazakhstan. Yeah, because the Russians are pretty good with, I don't want to go off topic, but anyway, the Russians are pretty good with getting people up and down. It might not be as comfortable as the Americans did it, but it works well. ISS is flying very low to Earth, but because of that, it's not geostationary. If we look into the sky, it's not in one point. In fact, it would be flying over the same continent or the same country dozens of times a day. If we want something, Earth rotates. So if we want something to rotate with the Earth, that from our point of view, even though we are always moving, we look into the sky and it stays in the same place, it's got to be pretty high. GPS satellites are also very low, but we've got lots of them, they're moving, so we always have 6, 7, 8, 9 in view, so that's good enough. Satellite dish on your house points in one direction. That means that satellite, let's say sky or whatever you get your tele from, has to basically, Earth rotates, how many hours for one rotation? 24 hours. So in 24 hours the satellite also has to do a big rotation around Earth. So the satellite always needs to make sure it's always in the same spot above people. So to do that kind of stuff, you've got to be pretty far away, which means if you want to use this for internet connection, it is possible. There are also internet telephones, for example, satellite telephones, for example. But the problem is the signals only travel with the speed of light. So by the time the signal goes there and gets beamed down again, we already had much more than a second pass. And the protocols the computers use, they are not made for such a big delay. So satellites possible, especially if we have to, let's say, there's a natural disaster, someone's on the North Pole or something like that. But usually we don't use satellites for communication. We use transoceanic cables. Yeah. So places like Europe and Asia, for example, again, this is an old map, but they're not that well connected. And usually if you add up all the capacity, you had more capacity going to East Asia to the USA. But if you visit a web page in East Asia, you don't know how the signal will travel. Will it travel still the USA, which is geographically farther, or will it travel to Russia somewhere closer, but maybe there's not so much bandwidth. So we don't know how our packets will travel. But we can send lots of bits per second. So connection, less communication makes much better use of our copper wires, because when you are not using it to send, your email or whatever you are sending, someone else can send information over the same copper wire in the same second. And in the end, on the lowest level, on the lowest layer, let's call it a layer, we got zeros and ones traveling. Yeah. And I think I mentioned Manchester code, so there might be different ways of sending those zeros and ones, but in the end, they're kind of traveling on that lowest level. And actually, let's talk about levels, or layers. I should call them layers. Let's think of a non-English speaking country. Give me the name of a non-English speaking country. Sweden. Good. So we got a Swedish professor here. Yeah, and he's a specialist in, you need to give me the name of our area. The topic area, not the geographic area.
Botany.
Botany. Okay, he's the big botany prof in Sweden. Okay, now we need another non-English speaking country. Somebody else? Difficult tasks. Is everybody asleep? Huh? China. Okay, so, and we've got another botany prof in China. Yeah. They want to talk about botany. Yeah. Because, I don't know, that there's a new tree being discovered or something like that. Yeah. They want to communicate with each other. Problem is, he only speaks Swedish. She only speaks Chinese. Yeah? Mandarin. Oh?
Mandarin.
Where are you from?
Shenzhen.
Shenzhen. So does she speak Mandarin or Cantonese? You decide.
Both.
Both. Good. So what do? They need some sort of translator. So there's a translator under our botany prof. And he speaks Russian. And Sweden used to be a neutral country, so they learned a bit of Russian as well. Or was Sweden neutral? I think it was neutral in the Cold War, I'm not sure. Maybe they were not neutral. Okay, so the prof actually wants to talk to the other prof in Shenzhen. But they can't, they're not in the same location, they don't speak the same language. So the prof gives the message to the translator will translate it into Russian, and that message will somehow go to the admin to the assistant in Shenzhen, and that translator will translate it back from Russian into Chinese. Yeah. So actually on a logical level, the two profs communicate with each other, but on a physical level, the prof communicates with the assistant. The assistants communicate with each other on a logical level, and the assistant then physically gives the message to the prof. And so there are different kinds of communication happening here on different layers. So how does that message actually get to Shenzhen? Do they send a letter? Do they use a fax machine? Do they send an email? I need somebody with fantasy here and who's not too shy. Email, good. So, yeah, they're gonna type it up on the laptop, gonna be sent over to the other laptop. So again, physical communication is actually between the admin here and the laptop. Logical communication is between the two laptops. So there are different layers of logical communication going on. And to be honest, maybe the two translators, maybe they don't know much about botany, they just know the words, they don't know what it means. So we've got a situation here where each layer provides a service for the layer above, and each layer can request a service from the layer below. This is the kind of system that we have in computing or everywhere. Now I could spin this down even further. You know, how is the computer connected to the internet? Yeah? Maybe they have broadband, maybe they are in a Wi-Fi. This could go on for quite a bit. And finally, when we are at the lowest layer, we've got zeros and ones. And to be honest, the zeros and ones, they don't care whether this is about botany and whether this has been translated into Russian or what's going on. And the translator doesn't care, is it botany? Yeah, the layer doesn't care about what the layer above wants. They just provide some sort of interface to deal with it, and they get on with their job. The email system doesn't care whether it's about botany or whether it's in Russian or whatever. So we've got the situation, and you know it's the same for you at home. You know, who's taking? Lots of you I can see are using tablets or small laptops. Now you're using them here. You're using them at home. Your laptop doesn't care. You know whether here it's I don't know a 2 gigahertz Wi-Fi, and at home you log into a 5 gigahertz Wi-Fi. Your laptop, or I should say, your email system doesn't care. Anybody here, are you using Outlook or for emails?
Yeah.
Outlook, yeah. So the Outlook software, if it's locally installed, not over a web interface, your locally installed Outlook software will be just a layer somewhere, and it can request a service from the layer below. And for your Outlook software, it doesn't matter at all whether the data is being sent with a 5 gigahertz Wi-Fi or with a 2 gigahertz Wi-Fi or with an Ethernet cable. It doesn't matter. You can replace that, and because all those different layers are encapsulated, they can work independently. Yeah? The prof doesn't maybe even know whether they send it by email or whether they send a fax or a letter. The prof doesn't care. All the prof wants to do is communicate about botany with the other prof. Yeah. So all those layers where this logical communication happens, they make use of layers below. They can request a service from the layer below. They can provide a service for the layer above. But we encapsulate everything. Yeah. Maybe not the best example, but everything is standardized. It doesn't matter for your, not the best example, but it doesn't matter for your laptop whether it runs on battery or whether it runs on from the power output. It will work in either case. We've got certain interfaces we provide, and this is also what we do in computing. And the zeros and ones we looked at, this is basically, why am I talking about this? Because you might say, I've been using a computer for 10, 20 years. I've never seen the zeros and ones, because they're happening on a lower level. And it doesn't matter for your machine, basically, what happens on the different levels. Any questions so far? Okay. In that case, I've got something exciting for you. Yay, I find it exciting at least. I want you all to think of two numbers. Please pick small numbers. Think of two small numbers, for example, 2 and 3. So tell me your two small numbers. I'll give you something then. Think of two small numbers. And please all think ahead of your small numbers. I don't want to wait every time. Right? Huh? 6 and 9. Don't you want smaller numbers? Pick smaller numbers.
2 and 6.
2 and 6, okay. Okay. You need those. And your numbers? Think of two small numbers and add them up. 3 and 4, so 7. And yours?
Let's go 1, 2.
Good choice. You'll make your life easy. Add them up.
1 and 3, 4.
You do it 4? Yeah. Just add them up. 1 and 2? Good choice. That seems to be a popular combination.
1.
Oh, and you all need a pen. Please get a pen out. One and 2. Okay, who's got the highest number? Who's got a number higher than 5? Oh no, you're the only one with a number higher than 5? What's yours?
7.
And yours?
6.
Ah, I might ask you to be my guinea pig then. So let's have a look at how computers work. Yeah? This is how it works on a very low level. Basically, this is kind of one step above. This is one step above binary numbers. Have a look at my instructions and see whether you can figure out how this works. Okay, let's try addition. Yeah. So what you see here is how a computer works on the most basic level. A computer basically can only add numbers and subtract numbers. Yeah. Everything else a computer does, multiply numbers, is based on addition. Yeah. 6 times 3 is 6 plus 6 plus 6. Yeah. You can do multiplication by kind of dissolving it into smaller additions. You want to do exponentiation, yeah? 3 to the power of 7 is the same as 3 times 3 times 3 times 3 times 3 times 3 times 3. And you can also then dissolve that into addition if you want. Yeah? So in the end, everything comes down to plus and minus. The whole thing, of course, went a bit out of control. In the 70s, that's what we did. But then we had graphical user interface. and we got voice recognition and all sorts of things, but in the end everything is just based on zeros and ones. And the point is, computers are just very fast at doing that kind of stuff. Yeah. But in the end, computers will do those kind of steps, but they can do them. Let's have a look here. This is a Wikipedia page. So 2017, let's do 2016. Yeah, an i7 Intel CPU can do 317,000 million. So 1,000 times a million is a billion. So 317 billion instructions per second. Yeah. So I'm going to ask you to do those steps, and it's going to take us a few minutes. Why are computers so fast? Because they can do billions of those in 1 second. Yeah, they're very fast but very stupid, but you can also build on that. So let's have a look at, come on, where are we? Yeah. So, if we tell the computer to do something, we've basically got our data register, which is a bit like the memory where we store numbers. And we've got our instruction set, which is the part of the memory where we store what the computer is supposed to do at the moment. And this is really, again, simplified, but this is how computers work. So if we want to do something specific, like we want to add numbers, yeah, we load the program how to add numbers into our instruction set. This is the program how to add numbers. This is the program how to subtract numbers. This is how to delete. This is how to copy. Yeah. So, for example, this is how to copy. I could write it in a different notation. Yeah. This is how copying looks in a different notation. And I said in the end everything is built on addition, multiplication. 3 times 7, you can resolve that in addition. Exponentiation, you can resolve it into multiplication, into addition. So the code just gets more complicated. So if you want to do exponentiation, you want to raise something to the power of something else, you just got lots more steps to do and lots more loops you go through. But in the end, everything is based on adding and subtracting numbers. So you need a pen. Please write down the instructions how to add numbers in your instruction set here on the left. So write J4 plus 1 minus 2, 0, 2. And I write them, look, and I'll show you how to do it.
Line 1, line 1.
So we got J4 plus 1 minus 2, 0, 2, J2, stop. Yeah. Now we loaded our program into our computer. And the two numbers you thought of, so what were your numbers were 7 together, what were they?
3 and 4.
3 and 4, yeah. You write them down here, 3 and 4. Let's do it this 3. 3 and 4. But because actually they will be changing all the time, it's not worth you writing them down. That's what your staples are for. Yeah? So put the number of staples in the right memory set. So if your numbers were 3 and 4, put 3 staples in the first field and put 4 staples in the second field. Yeah, that's supposed to be your staples. And I'll give you a minute. Can I ask you to come and we do it together? For everybody, just because you picked the biggest number. So if we do it on the board, it will take the longest, and the others can try to figure it out themselves. Or, they can look at us if they feel this is a bit too much. So the first instruction is J4. So J4 basically means we jump to position 4. Yeah. Now we follow the instructions at position 4. What are we doing? We are checking, is the content of data register 2 0? So how many are there? 4. Is 4 the same as 0? Yes or no?
No.
No. Okay. If the answer is no, we go to the next one. If the answer is yes, we jump 2 further. Okay, the answer was no, so we jump to instruction set 5. And what do we do? J2 means? Yeah? We jump to position 2. Okay. Plus 1. Add 1 to the content of data register 1. What about you do the fingers here? You know, the fingers are, that's what the pen is for. You always point with your pen at the position value. So point it to, and then I do the tablet thing. Yeah. So what do we do? Plus 1 means we add 1 to the content of data register 1. Yeah? Yeah, this is how a computer works. So we added 1. Okay, we finished our task. So we go to the next, we go a bit more to the side so that we don't block the view. So we finished our task. We do this one. What's this? So we subtract 1 from register 2. Yeah. Okay. Yeah. Okay, we go to the next one. What do we do? So is 2 the same? What's 2 at the moment? 3. Is 3 the same as 0? No. So what do we do?
Next step.
Yeah, next step. What do we do now? Yeah, step 2. So what's step 2? Should we swap? Can you be my assistant, please? My glamorous assistant. So step 2, what do we do now? Yeah, on the side. Yeah. So what do we do? Plus 1. Which one is plus 1?
The 1.
Yeah.
4 plus 1 is 5.
Data register 1 plus 1.
Yeah, no, here is minus 2, so 2 this minus 1, get 1 now.
Yeah.
And we got this step PC2XX, so we're back to the.
Yeah. So is 2 0? 2 is not 0, so we go back.
Yeah.
Yeah. So what next? So we're back at register 2.
Yeah, for the 1. And minus 1 to the second place. And also check if it's 0. It's not 0.
Not 0, yeah.
So we're back to the step 2 again. Plus 1 to the first. And minus 1 to the second.
Yeah, and now?
And check it's 0.
Is it 0?
Yeah, it's 0.
Now it is. So if it's true, we increase the counter by 2. Stop. We finished our task. Yeah. So this is a very simple task. We could draw it with 6 boxes. Yeah. Come on. Yeah. But if we do something like exponentiation, look how many boxes we need for that. Yeah. So it just gets more and more complicated. But in the end, all the computer do is it can add up numbers and it can subtract numbers. And everything we do is basically based on this. Any questions so far? Okay. So another handout for you.